Okay, so before I go to the surface integrals, I was going to show you one more example of a parameterized surface, and that's called a helicoid. All right, so what in the world is a helicoid? The parameterization is here: u cosine v, u sine v, v. All right. So what does that mean? Well, it's x squared plus y squared. I think you can see that is equal to u squared. Right, and that's it. It's not. There's nothing for v, right? V is not related to this, but it is because z is v, and then v and v appears here and here. Okay, so a way to think about this is, of course, there's something about a circle that's involved in this, but think of keeping one constant. Okay, let u be, for instance, 1. Okay, then what we have is cosine v, sine v, v. Okay, now does that sound familiar to you? Okay, yeah. If u is equal to 1, this is simply the your old-fashioned helix, right? So it kind of goes like this, right? This is where u is equal to 1, and so that's not too bad. So what happens if u is bigger, right? Well, if u is equal to, let's say 5 or something, then you have 5 cosine v, 5 sine v, v. All right, what's the difference? Well, it starts at, instead of 1, it starts at 5, right? And so maybe I will look at this in different colors here. Starts here, it's going to go around like this, right? And so u actually makes it grow. As u goes from like 1 to 5, you just take this entire space. And the whole thing is spiraling and moving up, okay? So what does it look like? Well, it does look like, and some people describe this as an infinite parking structure. So we have parking structures sometimes that are similar like this. You can just drive around and around and around, and then when you can come down in a spiral way. And so it is hard to describe what it looks like. The best way for you to try to understand this is to use your 3D graphing app. You can download a nice graphing app, an app on your phone, and you can sketch those things. And the answer is something like this. Okay, I hope you can see this. So the yellow surface is this helicoid that I was referring to. You can see the spiral thing, and as you go away from the center and away to the further edges, then you are increasing u. And then as v goes increases, then you're moving up in this infinite parking structure space. All right. The red horizontal plane is right there, just so you can see the intersection of this parking space with a parking structure with the horizontal plane. And so it is a sort of intricate and rather complex structure, but it is a interesting surface. It's actually it's not actually exactly a surface as in two-dimensional manifold. This is sometimes called a Riemann surface. All right, so let's get back to the section 6 and go and talk about the area surface integrals. All right, so the second part of this section deals with the surface integrals, and one specific example of that is how you find the surface area of a parameterized surface. Right, now let's go back to the curves again. This is from section 2 of this chapter. If you have a parameterized curve where t goes from a to b, and the parameterization is given as r of t, you can find the integral of ds, right? And this, remember, was the arc length and the length of this curve. And but the thing is, we never use s. I know s is the arc length parameter, but it turns out it's really just not very friendly in terms of actual calculations. So when we calculate, we actually use t, right? And then when you change from s to t, you have to insert something because ds is not the same as dt. But it turns out ds, remember, ds was ds dt times dt. They act like fractions. And this one happens to be speed. So we insert that speed, which is the norm of r prime of t, and then we put dt. This is how you find the arc length of a curve C. if you have a function defined at every single point on this curve C, and if the function is the real value function f, then you can integrate this, but you integrate again in terms of t, right? Remember, f is described in terms of t, not x and y anymore. And then we have to insert this speed, which was the norm or the magnitude of r prime, and then the t. All right, this is ds, okay? This is ds. Now we're going to have to do something similar for this. What is it that we need to do for a parametrized surface? So I should say before we go further, if you're looking for the surface area of S, this is going to be represented by this double integral over the surface S of d, well, we had ds here. This is going to be called d capital S, right? And, the question is, we don't know what that is yet, okay? And that's what I'm about to explain. If you have a function f, okay, then we can talk about the surface integral of f on S, okay? And so this is going to be the double integral over S of f and then ds. All right, so it begs the question, what in the world is this ds? Okay, so here I am going to tell you what that is. All right, you have the domain on the UV plane, which is typically rectangular, not always, right? And the way you try to figure this out is just as we did with all the other times when we first talked about integrals, right? What do you do with this domain or interval? Well, we divide them into smaller subintervals, and that's exactly what we're going to do. I'm going to use some lighter color here. We divide this into a bunch of smaller pieces, okay? So, and we don't have to, but we can just divide them into small rectangular pieces, right? And then of course the image is going to be somewhat like this. Maybe we don't know what it looks like, but it could be curved here, whatever, right? And so that's what it looks like. Now we pick the one of them. Let's say this is the ith, so this is a partition of the rectangular region D, and we pick the ith rectangle. Ith is I with a th, right? So this is a very small rectangle, and this has an image maybe over here, okay? And so in the DV, or in the UV plane, we are going to do dA, which is dV du or du dV, right? Assuming that we are using rectangular coordinate system. Now, after the transformation, that image of the ith triangle is going to be this. But this is going to be something very much like a flat plane. It's not quite flat, but remember the whole idea of subdivision is that you can make things almost flat, assuming that this is a smooth curve, all right? And what do we know about this? Well, we know that this vector here, let's say this is the RU. Okay, so the partial derivative with respect to u is RU. Partial derivative with respect to v is RV, right? So you have these two vectors that are tangent and are on the tangent plane to S at this particular point. Okay, we're talking about that. And then how do you find the area of this? That's a question, right? So this is the ith rectangle. So what we are interested in is to find the image, find the area of the image of the ith rectangle in the UV plane, which is this. And how big is that over here after the transformation? And the answer, do you remember this? This is, what is that? Okay, well, the point is that this is very much like a parallelogram. Okay, and in fact, infinitesimally, if you take a smaller and smaller rectangular region, this will become parallelogram. And it's a parallelogram where RU is one side and RV is the other side, right? They are adjacent two sides. And the area of a parallelogram created by two vectors as adjacent to adjacent sides is what? So the area of this parallelogram is, yeah, if you remember, you take the cross product, right? And the cross product, by the way, will be perpendicular to the tangent plane, plane tangent to S at this particular point, okay? And the magnitude of the cross product was, yeah, that's, I mean, this is what we learned in chapter 2. This is exactly the area of the parallelogram where RU and RV are adjacent sides. So this turns out to be my key here, okay? This is the delta of SI, the area of the ith rectangle. And of course, what we do is we just sum this up, you know, for all the small rectangular regions. And so, and then we define the limit, and that becomes your integral, the surface integral, right? So ds is going to be here. This is really cool. It's going to be RU cross RV, and you take the magnitude of it and then put dA in it, okay? So, and of course, this dA is either du dv or dv du over this domain D, okay? So that's how you convert this. Just like over here, we had to insert the speed, which was the magnitude of r prime. And it's very similar, right? I mean, it is the magnitude of a vector. And that vector happens to be a normal vector, which is the cross product of the two partial. And I also want to note that, because this will be useful later, note that RU cross RV is perpendicular to this space or the surface S. All right, so here is the conclusion, and maybe I should write this in red. The area of the parametrized surface S is defined as the double integral over S of ds. But what I mean by ds is basically you take this double integral and then insert that magnitude of the cross product and then dA. Now dA is taken over, watch really carefully here. I'm not gonna put S over here, okay? What am I going to put? You're actually integrating with respect to U and V, so this will be D. Okay, so you take the surface area, you're looking for the surface area of the surface, the parametrized surface S, but you do so by taking the double integral over the domain D, which belongs to the UV plane, all right? And the adjustment is made by that number here, whatever that number is. And sometimes that number could, or the expression could depend on U or V, all right? So that's the area of the surface. Now, if F is defined on S, okay, so at every point of S, which is, you know, the point X, Y, Z on S, then the surface integral of F on S is this double integral of F ds. This is a capital S, okay, right? I mean, that's what we mean by the surface integral. And so what is that? Well, that would be F described in terms of U and V. I have to describe this in terms of U and V. And then we insert that magnitude of the cross product RU cross RV. And then dA, the entire integration here takes place not on the surface S, but on the domain D. Okay. Now, let's say you have this surface S. Okay. So you have a domain D on the UV plane, parameterized by R to become a surface S, right? And every point X, Y, Z has a function defined so that at every single point of S, you have a real valued function, right? So you have a value defined on this. What does this represent? Well, if F is the density, what we are doing is actually, you know, just adding up all the density at a single point and then adding them together in a continuous way as opposed to a discrete way. So this will be the mass of that parameterized surface S with density D. I hope this makes sense, right? A lot of times, you know, students figure out how to take the integral and they have no idea what they're trying to find. You know, what does this mean? Well, I think the best way to understand this is if F is considered the density, this will give you how heavy this surface S is, or the, you know, mass of the surface, the parameterized surface S. It has many other applications, notably the next thing we study, which is the flux integral. But right now, we are not talking about the flux. We are talking about the either finding the surface area of S or finding the surface integral on S when the function, the real valued function f is defined on at every single point x, y, z on this surface S. Let's do an example of this. Several examples of this, right? Number one, find the area. I will write down this question. All right, so this is the first example of the parametrized surface I showed you earlier. You remember this? This is a radius 3 vertical cylinder of height 2. Okay, or V is Z, which goes from 0 to 2, and U, of course, goes from 0 to 2 pi, right? By the way, what is the surface area here? Well, you already know the answer to it because if you just cut it, cut it right here, let's cut it over here, and then it becomes a long strip. If the radius is 3, the length or the circumference is 6 pi, the height is 2, and so the answer is going to be 12 pi. We know the answer to this already, right? Well, let's use what we've just learned. The area is found by the double integral over S of ds. This is the definition of what the area is. And so to do that, you have to find Ru and Rv, and you take the cross product of it, and you take the magnitude of it. All right. And after you do a few problems of this nature, your hand will automatically start writing these kind of things. Ru is equal to, Rv equals to, Ru cross Rv equal to, and then strategically I write this, vertically. I think you can see why. Because if you write this right underneath each other, this Rv right underneath of Ru, it's easier to do your cross product visually. All right. So what is Ru? Well, that's negative 3 sine U, 3 cosine U, 0, right? No problem here. Rv is 0, 0, 1. That's even easier. The cross product is you do the crossing, like all that. It's 3 cosine U, and then 3 sine U, and 0. Okay, so the middle one is positive because you have the double negative here. It's negative of negative 3 sine U, right? Okay, so what's the magnitude of this? Well, that's pretty easy. That's 9 square root of 9 cosine square. Should I write this? Yeah, should I write this? Yeah, 9 cosine square U plus 9 sine square U. And of course, that's the square root of 9, otherwise known as 3. Okay, so this is a nice, right? So basically what we have is this. Now remember, this is Ru cross Rv. Oop, that's not parentheses. It's going to be the magnitude of it. And the A, remember this A has to do with the D. D is defined by this, okay? So the answer is U goes from 0 to 2 pi. V goes from 0 to 2. Now you have this number 3 in here, and then dv du. Okay, now it's very important for me to point out these numbers, u and v, the upper and lower bounds of u and v will appear here. Okay, because when you're trying to integrate over S, because of the parametrization, you are actually integrating over that pre-image, the domain. Okay, so these come from your picture of D. Just like in the line integral, you never use ds. We always went back to dt because t was the parameter, and so the same thing happens here. And in order to convert from ds to da, we have to make that little adjustment, which is called the it's a part of the differential, right? And that is the magnitude of the cross product Ru cross Rv. Everything else here is easy, right? This is just the integral from 0 to 2 pi of 3 times 2, because there's nothing to integrate, you just get 2. And then this is 3 times 2 times 2 pi. And of course, the answer is 12 pi as we expected. All right, so that's how you find the area. Let's go to the next example. Actually, at this point, I think I'm going to do example slightly different from what I was going to do. All right, so let's say we have this triangle, okay? So this is 2, 2, and 2. This is a equilateral triangle. All right, this is my S, okay? So what happens here? Let's say the question is find the area of S. Okay, and I'm going to give you a little hint here. Z is a function of X and Y, and Z in this case is defined as 2 minus X minus Y. All right, so the point is X plus Y plus Z. Is that right? Yeah, X plus Y plus Z is equal to 2. And so this is actually the surface of defined by, it's a plane defined by X plus Y plus Z is equal to 2 over some region. Now the region is actually going to be like this, X and Y. If you look at this from the top, you know, this is what it looks like, right? So this is going to be my domain D. I haven't given you the parameterization yet, right? So let me give you a parameterization. Maybe you can figure out the parameterization of this. Because I talked about this, right? If f is defined as a function of X and Y, then you can, or you don't have to, but use the parameterization, most obvious parameterization, okay? And which is R of uv is equal to, you let u be X, v be Y, and Z is basically that thing, 2 minus X minus Y, except I am not allowed to use X or Y. So this is 2 minus U minus V. Get that? Okay, then RU is what? 1, 0, negative 1. RV is 0, 1, negative 1. Okay, and so the RU cross RV is equal to, what is that? It's 0 minus negative 1, it's 1. And then you have 0 minus negative 1, that's 1. And then you have 1, right? Okay, so it looks like it's just 3. Well, I mean 1 comma 1 comma 1, and the magnitude is not 3, of course. It's the square root of 3, right? All right, so now we have to figure out what the limits are. Okay, limits. So this is X, which is U, Y, which is V, right? And so you can define it just like what we did in chapter 5. Let U be from 0 to 2, okay? Then V has to depend on U, and sometimes you have to make it this way because not every domain D is rectangular. So here in this case, V goes from 0 to, well, this line is, you know, Y is equal to what, negative X plus 2. So it's V is, you know, negative U plus 2. Okay, that's what you'd have to do. So the area of S is going to be the double integral on the surface S of the S. This is the definition of the area. But if you're trying to calculate this, this is like this. U goes from 0 to 2, V goes from 0 to negative U plus 2, and then square root of 3, and then dV du. The rest should go straightforward. It's a square root of 3. And then since you're integrating with respect to V, you just have negative U plus 2. Okay, so let's just take this out, negative 3, right? And then we can integrate this negative U square over 2 plus 2U going from 0 to 2. And this will be the square root of 3. And then negative 4 over 2, that's 2. Plus 2 times 2 is 4. So this will be 2 square root of 3. And that is correct in terms of the area of S. Okay, you can verify this, by the way. You know, if you have a equilateral triangle, and let's say I think the sides are all 2 times the square root of 2, right? Because it is the diagonal of a 2 by 2 square, right? So you can do this by hand, and you can see this is 60, 60, and you can find the height, and you will be able to verify that this surface S indeed has the area of the 2 times the square root of 3. Okay, and I might say in general, if R of UV is defined as UV and F of UV, then RU is clearly 1, 0, X, Fx, right? So remember, because U is the same as X, and RV is 0, 1, and then you take the derivative of F with respect to V, which is Y. So this is what you get. And then RU cross RV. Right? If this is, again, in general, if Z can be described as a function of X and Y, then this is what happens. And then the cross, I'm generalizing what we just did here. If you do that, then the first coordinate is going to be what? It's going to be negative Fy, Fx, okay? And then the second coordinate will be Fy, but you have a minus sign, so it's negative Fy. And the last one will always be equal to 1. All right, so in this case, if Z is a function of X and Y, F of Xy, then the norm or the magnitude of RU cross RV will always be the square root of 1 plus Fx square plus Fy square, okay? And then you put dA at the end of this. So that is simply the case anytime you have this kind of a parameterization. All right, let's go back to sort of a main part of this lecture here. This time I want to go into the surface integral, right? So find the integral, the double integral of f ds, where f of x, y, z is x squared, and s is, and I will show you what s is. All right, so S is a quarter of a cylinder, right? So this is X, no, that's Y, this is X. So of length 5, okay? So, and the radius 4, right? So you can think of a object, maybe a piece of metal that is used as a part of a car or something, and that's, it's curved. It's a 1/4 of a cylinder, like this. Okay, so this is my surface S. And you can think of F as a density, all right? So in other words, it gets more heavier and heavier as X increases, right? So this part is much heavier than this part, and so on. So how heavy is this? What's the mass of this piece of whatever that is, metal or something? Okay, and that would be the answer to this question, the double integral of F on surface S. All right, so what do you have to do here? Well, first I have to parameterize this surface, okay? And how do you do that? Well, let's try to parameterize this. I have to have y square plus z square is equal to 16, right? Now, x is independent. So x can be, r of u, v. X is totally independent of y and z. So I am going to let x be u, okay? And u is going to go from 0 to 5 because that's what the picture shows. And then I need to make sure that y squared plus z squared is 16. There's a nice way of doing this. It's 4 cosine v, 4 sine v, as v goes from 0 to 2. Oh, not 2 pi, because I'm just talking about a quarter of the circle. That's pi over 2, right? Yeah, so that would this would describe this surface S. It's a good parameterization. Right. Now, in general, parameterizing a given surface could be very difficult. All right, so I'm not going to give you a very complex surface to parameterize, and that's why you need to be familiar with those examples I gave you earlier. All right, can you parameterize, for instance, a cylinder? How about a cone? How about the sphere? And how about if Z can be described as f of xy? So those are some of the basic models to follow when you try to parameterize surfaces. Okay. All right. So with this, you can do RU, which is 1, 0, 0, and then RV, which is 0, negative 4 sine V, 4 cosine V, and RU cross RV is equal to, and you can see it's 0, and then the second component is negative 4 cosine V, and then the last component is negative 4 sine V. Okay, and I think you can tell without doing a lot of calculations here, the norm of this vector is what? Square root of 16, which is 4, right? All right, and so now I also have to describe f of x, y, z in terms of u and v. That's x squared. Well, that's nice because x is simply u, so that's u squared. All right, and therefore, now we can evaluate this surface integral, which represents the mass of this parameterized surface S, in terms of, well, it's a double integral over S of f ds, but this will now become, and notice here, v goes from 0 to 2 pi over 2. U goes from 0 to 5. And it doesn't matter which order because UV, this is a rectangular region D. And then you have U square, right? And then what else do you have to have? You have to have this 4 here, right? Because that is the thing you have to insert before you do du dv or dv du. In this case, 0, 5 is an inside, so I do du first and then dv next. Right. Did you get this? All right. So this part is the norm of RU cross RV, and this part is dA, and this is F. Okay, and that is the integral that I need to have. And this part is over the domain D. Your upper and lower limits are defined accordingly. All right, so this is going to be, it's 4, and then you have U cubed over 3. And then going from 0 to 5 dV. This whole thing is going to be constant. Okay, so it's 125 times 4. That's 500 over 3, and then pi over 2, right? So this would be 250 pi over 3. And this is the answer to the question of the mass of this parameterized surface S. Okay, so whenever you have a function f defined at every point x, y, z of the surface S, we can integrate, and that makes sense. For instance, you can interpret that the surface integral as the mass of the surface S. Okay, now what happens if at every single point of this surface S, okay, you can find how there is a fluid inside of the cylinder, and that's coming out. S is maybe like a membrane or a film or a filter or something, and the fluid is coming out from the inside of a cylinder to the outside. Maybe energy is flowing from the inside to the outside, right? And it is described as a vector field. Then for each point x, y, z, we can figure out how much of the stuff, the fluid or the energy, is coming out of the cylinder at this point, right? And the way you have to calculate is if the fluid is the flow, or the if the radiation flow, whatever is described as a vector field, then you have to find a normal component at every single point, right? And you find a normal component if you integrate the normal component of the flow at every single point. You actually get the flux, the total flux of the energy or the fluid over the surface or across the surface S. That's flux. So the flux is actually, what is that? Well, it's basically the surface integral, right? Where you are integrating something, normal component of the vector field. That's our next topic as we move into the flux integral.